Every second, thousands of bridges around the world hold up trains, trucks, and people. Yet, most of us never think about the silent war they're fighting. Gravity pulls down with crushing force. Wind pushes sideways, sometimes with hurricane strength. Traffic hammers them with constant vibration. So why don't they collapse? The answer isn't just strong materials, it's the hidden physics of clever design. Engineers have spent centuries discovering nature's secrets about forces, shapes, and balance. In the next few minutes, you'll see bridges in a completely new way, understanding the invisible forces that keep us safe every single day. Ready to decode the science that holds up the world? Here's the journey ahead. First, we'll crack the code of tension and compression, the two fundamental forces fighting inside every bridge. Then you'll discover why triangles are stronger than any other shape and why engineers are obsessed with them. Next, we'll compare four major bridge types: suspension, arch, beam, and truss, and see how each one fights gravity differently. After that, we'll explore the science behind dangerous wobbles and resonance, the phenomenon that can shake bridges apart. Finally, we'll peek inside the testing labs where engineers torture bridges before anyone crosses them. By the end, you'll never look at a bridge the same way again. Let's start with the hidden forces inside every structure. Imagine pulling a rubber band. That stretch is called tension. Now picture squeezing a sponge. That squish is compression. Every bridge component faces one of these forces, or both at once. When a truck drives onto a bridge, the deck sags slightly downward, putting the bottom in tension, like stretched fibers, and the top in compression, like squeezed concrete. Materials behave differently under each force. Steel is fantastic in tension, which is why it's used for cables. Concrete is superb in compression, perfect for pillars and foundations. Engineers carefully place each material where it's strongest. Get it wrong, and cracks appear. Then failures cascade. But match the right material to the right force, and your bridge can stand for centuries. Now, here's where geometry becomes a game changer. Squares and rectangles collapse easily. Push one corner, and they deform into parallelograms. But triangles? Completely rigid. Once you fix three sides together, the shape locks and cannot change without breaking a side. This is why you see triangles everywhere in bridges, towers, and cranes. Engineers call structures made of triangles trusses, and they're shockingly strong for their weight. When force hits a triangle, it distributes instantly across all three sides. Tension here, compression there, perfectly balanced. The Eiffel Tower is basically 18,000 iron triangles stacked cleverly. Modern truss bridges use this same principle, creating lightweight frames that punch far above their weight class. Nature figured this out too. Look at spiderwebs and honeycombs. Next, let's compare how different bridge types use these principles in completely different ways. Beam bridges are the simplest, just a flat deck resting on pillars, like a plank across a stream. Great for short distances, but they sag in the middle if too long. Arch bridges curve gracefully, channeling weight downward and outward into the ground through compression. The ancient Romans mastered these. Suspension bridges hang from massive cables draped over towers, using tension in the cables to support the deck below. Perfect for spanning huge distances like San Francisco's Golden Gate. Truss bridges build rigid, triangular frameworks above or below the roadway, distributing forces efficiently for medium spans. Each design solves a different problem: distance, terrain, materials available, and cost. Engineers choose based on what forces dominate and what the landscape allows. But all bridges share one deadly enemy: unwanted motion. Bridges aren't frozen in place. They're designed to flex slightly with wind, traffic, and temperature changes. But there's a dangerous zone called resonance. Every structure has a natural frequency at which it wants to vibrate, like a tuning fork. If an external force matches that frequency, say wind gusts or marching soldiers in rhythm, the vibrations amplify dramatically, swaying larger and larger. The Tacoma Narrows Bridge famously twisted itself apart in 1940 when wind matched its resonance frequency, captured on shocking film. Modern engineers add dampeners, special weights, and aerodynamic shapes to break up these rhythms. Some bridges have giant pendulums hidden inside their towers that swing opposite to the bridge's motion, canceling vibrations. It's a constant chess match with physics. So, how do engineers test all this before opening day? Some bridges face conditions you'd never imagine. The Millau Viaduct in France soars 343 meters high, taller than the Eiffel Tower, where winds scream across the valley at speeds that would knock you over. Engineers designed split decks that let wind pass through instead of pushing against solid walls. In Alaska, the Tanana River Bridge must handle temperature swings of 80 degrees Celsius between winter and summer, causing metal to expand and contract dramatically. Special joints absorb this movement. Japan's Akashi Kaikyo Bridge spans nearly 2 kilometers and must flex during earthquakes without snapping. Its cables are thicker than a human torso. Meanwhile, the Sunshine Skyway in Florida uses massive concrete fenders to deflect ship collisions after a cargo vessel destroyed the original bridge in 1980. Each extreme teaches engineers new lessons. But what about the myths surrounding bridge safety? Myth 1. Bridges are either safe or dangerous, period. Truth. Every bridge is inspected regularly and rated on a scale. Even deficient doesn't mean collapse is imminent, it means repairs are needed eventually. Myth 2. Marching soldiers still break bridges by walking in step. Truth. Modern bridges account for rhythmic loads. This was only a concern for early wooden suspension footbridges. Myth 3. Bridges get stronger as they age. Truth. The opposite. Materials fatigue, corrosion eats steel, and cracks propagate slowly. Myth 4. If a bridge sways, it's about to fall. Truth. Controlled movement is intentional design. Rigid structures crack under stress. Myth 5. Bridges are built to never fail. Truth. They're designed with safety factors, meaning they can handle several times their expected maximum load, but maintenance is essential. Understanding the truth helps us appreciate the real engineering involved. Think you can test your new knowledge? Let's see if you've been paying attention. Question 1. Which force stretches materials? Tension or compression? Pause and answer. It's tension, like pulling a rubber band. Question 2. Why are triangles used in trusses? Because they're the only shape that's naturally rigid and can't deform without breaking. Question 3. What's resonance? It's when an external force matches a structure's natural vibration frequency, causing dangerous amplification. Final question. Which bridge type uses cables in tension to support the deck? That's a suspension bridge, like the Golden Gate. How did you do? If you got 3 or 4 right, you're already thinking like an engineer. If not, no worries. These concepts take time to sink in. The important part is understanding that bridge design isn't magic. It's physics applied with precision and creativity. So why does any of this matter to your everyday life? Bridge engineering doesn't just move cars. It connects communities, enables trade, and saves lives. When a bridge fails, like the Morandi Bridge collapse in Genoa in 2018, entire cities are cut off, emergency services are delayed, and economies stall. Good bridge design means ambulances reach hospitals in minutes instead of hours. It means fresh food arrives at markets. It means you can visit family across the river without a 3-hour detour. Every principle we've discussed, tension, compression, triangles, resonance control, translates directly into human safety and prosperity. Researchers estimate that efficient bridge infrastructure adds billions to global GDP annually by reducing transport costs and time. And as climate change brings stronger storms and flooding, engineers are redesigning bridges to handle conditions their predecessors never imagined. The science keeps evolving. Speaking of evolution, what don't we know yet? Despite centuries of bridge building, mysteries remain. Scientists are still perfecting materials that repair themselves when microcracks form, using embedded bacteria or capsules that release healing compounds. We don't fully understand long-term fatigue in novel composite materials. Will carbon fiber bridges last a century like steel? Researchers are exploring smart bridges with thousands of sensors that monitor stress in real time, predicting failures before they happen using artificial intelligence. There's debate about whether we can build bridges that adapt their shape actively, like muscles responding to loads. And as we plan structures for Mars or floating ocean cities, we're entering completely unknown territory with different gravity, no atmosphere for wind loads, and materials we've never tested at scale. The physics we've covered today is just the foundation. Tomorrow's engineers will push even further into the unknown, and maybe that engineer will be you. Let's recap this incredible journey. You've learned that bridges fight constant battles against tension and compression, and engineers match materials to forces with precision. You discovered why triangles are structural superheroes, locking forces into rigid, efficient shapes. We compared suspension, arch, beam, and truss bridges, seeing how each tackles different challenges. You explored the dangerous phenomenon of resonance and how dampeners keep bridges stable. We busted myths and revealed how engineers test bridges to destruction before you ever cross them. And you glimpsed the future of self-healing, smart, adaptive structures. Next time you cross a bridge, pause for a moment. Feel the physics at work beneath you. Appreciate the invisible calculations keeping you safe. If you enjoyed unlocking these secrets, hit subscribe to Easy Learning. We make complex science simple and fascinating. Drop a comment. Which bridge type is your favorite and why? Thanks for watching, and keep learning.